are of this form, right? S here, like here S is 1, here S is 2, here S is D minus 1, right? So these terms here are like this. So this belongs to H, right? Because these terms are just these. So this belongs to H, right? So therefore, now B originally we said was a member of K, right? So if B belongs to K, B belongs to H, right? If B belongs to K, B belongs to H. Now that's the definition of a subgroup, right? Because it could have been any B. So that means that this subset, subgroup, this supposed subgroup, K is a subset of H, okay? But by assumption, the size of K is D, right? We're trying to show that this second subgroup of the same size, the same size as this divisor, this factor D of n, where n is the size of your group, your parent group, right? So we assume they're the same size, so the order of K is D, and the order of H is D, so this and this are the same size, right? But yeah, so we know that. So the only way this and this can be compatible, if K is a subset of H, but the two sizes, the two sets are the same size, they have the same number of elements, the only way that can be true is if they're the same, right? So we proved it. So K equals H. So this supposedly second different subgroup is not different, because it's the same. We proved it's the same, right? Therefore, if your group is cyclic, then if you create a subgroup whose size, whose order, divides this, there's only one. There'll only be one that can do that. Only, right? It will be a cyclic group of this form. Okay. Right. That's the last of the theory. Now, just to finish off quickly, I'll give you just another taste of creating cosets, because there's a chapter on cosets. It's straight out of the text, of course. You're given a group. We're now in the context of complex numbers. So you're given a group here of order 6, right? And you're told that these members of the group are each multiples or powers of the 6th root of 1. Right? Now, so in other words, if something to the 6th equals 1, which is the same thing as e to the 2 pi I, right? So theta would be e to the 2 pi I divided by 6. Right? So here it is here. So we obviously have a cyclic group here, right? And theta, this is your generator, because to the power 1 to the power 2, that's the definition of a cyclic group, right? So that's your generator, and here's a subgroup. It's you can show fairly readily. You know how to prove that a subset is a subgroup. Right? You go through the three tests. You don't have to test for associativity. That's inherited from the parent group. But you test: is there a unit? Is it? What are the three? This is the unit, the inverses, and closure. Okay. So this is a subgroup. I assume you can see that pretty easily. Okay, now find the left cosets. Well, one of them is just H itself. Why is that? Because EH is just, now in this case E, the unit is just 1. Right? So EH is just H, because if you multiply each of these by 1, nothing changes. Right? So E of H is H. So H is one of your cosets. Alright, so now let's find another one. So let's find theta of H. That's one of your members of your set G. Right? Theta's a member. So theta of H, that's a coset. Well, you just multiply each of these on the left by theta, so you'll get theta, theta cubed, theta the fifth. Right? That's another coset. Now watch. The two cosets, if you union them, rubbed it up, remember the theorem that your set G is a union of disjoint cosets. Remember that? Well, your G here, if you union that with that, those two sets, cosets, you'll get the whole group, right? You know, those three and those three, unioned, will give you this. So that's all the cosets there are. Any other coset would be equal to this or this. So that's it, right? So there are only two cosets. Okay, well that's the end of the theory part. So next session will be problem solving. So let me, before I finish off, say a little bit about the next lecture. Now, well, we've rubbed it off, but now that we have Lagrange's theorem, and we know that the order of an element divides the order of the group, also they're sort of equivalent but very, very powerful. We now have some very powerful tools to start investigating the different types of group you can have of a given order. Where if you know the order of the group, you can start deducing how many different kinds of group you can have for that order. Now, I mentioned this a bit before, but so the next chapter will be looking into the different kinds of groups you can have for group order up to 8, including 8. Right? So immediately we know that groups of order 2, 3, 5 and 7, because they're odd, the order of the group is odd, an odd number. Therefore, those groups have to be cyclic. Right? That's all there is. There are no subgroups, no proper subgroups. And so the analysis then boils down to looking into what's left over in a sense. Order 1, that's trivial, which is a trivial group, so that's the end of that discussion. 2, 3, they're prime, so we need to talk about order 4. So a lot of discussion about groups of order 4. 5 is prime. Order 6, some discussion. 7 is prime. And 8, some discussion. Okay, so next session will be problem solving.